All right, hey AP Chemistry. So I got requests to do some of the sample problems that are in your Unit 6 Important Information Part 2 notes. I'm going to try and do questions 2 and 4, and if time allows in this video, I'll do 8. So for question number 2, it says, what mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? What mass of CO2 is produced? Now this is butane. Okay, we're going to need this later, but I'm going to tell you that the molar mass of butane is 4 times 12 plus 10, right? 4 carbons, and then each hydrogen's 1. Boom. Molar mass we're going to use is 58 grams per mole later, okay? All right, so I gave you that 1.5 times 10 to the third kilojoules of heat is produced. That means it's released, which means it's negative. And I want to know what mass of butane is required to give me that energy. Well, remembering stoichiometry and enthalpy of reaction, for every 2 moles of C4H10, there is negative 5316 kilojoules that come out of the reaction. So we're going to use that relationship for our calculation. So I'm going to start with 1.5 times 10 to the third kilojoules, and we're going to make that negative. It was released, right? Kilojoules of heat. And I know for every 2 moles of C4H10, there's negative 5316 kilojoules. Kilojoules per mole of reaction, or for the reaction, I need 2 moles of C4H10. So if I do this math, 1.5 times 10 raised to the third, I'm just going to, the negatives are going to cancel out. Multiplied times 2, divided by 5316, I get 0.564 moles. I didn't do any sig figs, it doesn't matter. Moles of C3H8. All right, I'm just using 3 decimal places. The question asks for mass. Well, remember, to go from moles to mass, I multiply by the molar mass. Or I'll just do dimensional analysis. So 58 grams of C4H10 for every 1 mole of C4H10. You could have all done this in one step too. And so multiplied by 58, I get 32.7 grams of C4H10. And then the question also asked, what mass of CO2 is produced? Well, we have information. We have how much energy came out. We could use that again. For every 8 moles of CO2, that much energy is required. Or I could use the mole ratio of C3H8. For every 2 moles of C4H10, there are 8 moles of CO2. Doesn't matter, but these moles are what are in this reaction. So doesn't matter how you do this, I'll use the 0.564 moles of C3H8, and I'm going to use the mole ratio. These moles are what's in this reaction right now. For every 8 moles of CO2, there are 2 moles of C4H10. And if I do this math, I'll do 0.564 times 8 divided by 2. I get 2.256 moles of CO2. And then the same idea, if I want to know grams, I multiply times the molar mass. Prove to yourself, but the molar mass of CO2 is 44. 44 grams of CO2 for every 1 mole of CO2. And I get times 44, 99.26 grams of CO2. That is how you do question number 2, right? This all has to do with stoichiometry and mole ratio, and now we have mole to energy ratio. I'm going to jump over to question 4. Question 4 is a limiting reactant problem, okay? If I have 2 moles of H2S and I react it with 3 moles of O2, I get 2 moles of H2O, 2 moles of SO2, and this much energy comes out. Based on the reaction above by the chemical equation shown above, what is the amount of heat released when 4 moles of H2S reacts with 9 moles of O2? Let's remember how to do limiting reactant problems, or our setup. And this time, I'm going to make energy a product, plus 2SO2 plus 1120 kilojoules. Energy is a product. If I have negative energy, that means energy is a product. So I'm going to write it as a dash. Okay? If you remember our BCA table, for this limiting reactant problem, or how do I know it's a limiting reactant problem? If I give you two amounts of reactants, automatically it's a limiting reactant problem. And a limiting reactant, I have to find the one that limits the amount of product formed. For an exothermic reaction, negative energy means exothermic, energy is a product. So whichever one of these reactants gives me my least amount of energy, that's going to limit the amount of energy that comes out of the reaction, and that's how much energy actually is coming out of the reaction. So I have 4 moles of this, 9 moles of this, and initially I don't have anything. And then there's going to be a change. Now, let's say I used up all of my H2S. If I used up all of my H2S, for every 2 moles of H2S, I get 1120. If I have 4 moles, if I use all 4 of them, I will have twice the amount, 2240, that comes out. But if I have 3 moles of O2, I get this much energy that comes out. 9 moles is 3 times the amount. So if I were to use all of it, this is if I use all, I should have 3 times the amount, times 3, which is 3360. Which of these do I choose as my lowest amount of energy that comes out? Or like if we treat this like a product, I choose my lowest energy, the one that has the least amount, which is 2240. So that's the correct answer. For a limiting reactant problem, you choose lowest moles of product. In this case, lowest energy I choose. So you do both mole to mole ratio. I choose my lowest moles, or my lowest amount of product, lowest amount of energy, and that's going to be how much energy comes out of this reaction because it's limiting. I'll also jump over to question number 8 now. Great. Question number 8 is an enthalpy problem. Okay, very simple. We've done this a bunch of times in class. A calorimeter was used to determine the molar enthalpy of solution of AlCl3. Just so you know, we're going to need the molar mass of AlCl3. It is 133.43. Later on, I'll use this. 34 grams per mole of AlCl3. All right, when a sample of AlCl3 was dissolved in water, the following data were collected. So I put 10 grams of AlCl3, and I have this much water, and the temperature was initially at 20, and then it went to 46.3. To remind you what we talked about in class, now get in the habit of, if I don't talk about the calorimeter, if I don't ask about the calorimeter constant, we could use the mass of the solution to calculate Q. If you just use water, that's fine. You'll get a very similar answer, but we're going to use the mass of the solution. So to get the enthalpy of the solution, I could get the Q of the solution, which is equal to M of the solution times C times delta T. We're going to assume the specific heat capacity of the solution, because it's mostly water. It's 4.184 joules per grams degree Celsius. Also, make a note here that my temperature increased. That means energy was released. And so we're going to have to make this energy negative later. So I'm going to put negative Q of the solution. Whatever happens to the surroundings, which is mostly this water solution, the negative is happening. So I'm going to make this negative Q of solution. So for my mass of my solution, water has a density of 1 gram per milliliter, so this is basically 250 grams. My mass of my solution is going to be 260 grams. Specific heat capacity, we'll just say the specific heat capacity of the solution is 4.184 joules per grams degree Celsius. You'll be given that information. And my delta T is 46.3 minus 20 degrees Celsius. Final minus initial. A lot of you didn't do that or might forget that I have to do final minus initial. So if I do all this calculation, My delta T is 46.3 minus 20. That's about 26.3 degrees Celsius is my delta T. I multiply that by 4.184 times 260, and I get negative 28610.192 joules. I eventually want kilojoules per mole for AlCl3. I'm going to convert this to kilojoules by dividing by 1,000. So now I have 28.61 kilojoules. If I want delta H of solution, I take Q of solution and I divide by moles of the solute that I dissolved. Right, so I use 10 grams of my solute. This enthalpy of solution comes from dissolving my solid in the solution. So I want to know how many moles of solute did I dissolve, is what I use for my solution. So I'm going to do that math over here. I told you the molar mass is 133.34, and I gave you 10 grams. Moles, which is N, is grams over molar mass. So 10 grams divided by 133.34 grams per mole. 10 divided by 133.34, I get 0.07499 moles. Now I'm going to take my Q that I got up here is 28.61 kilojoules, and I'm going to divide it by the moles of solute that got dissolved, 7499 moles. And this is going to give me my enthalpy of solution in kilojoules per mole, divided by 0.07499. Boom. 381, make it negative, I forgot, make it negative 381.52 kilojoules per mole. That is how you solve question number 8. So I'm hoping these questions could kind of help you get through the rest of the questions. Make sure you do question number 9. Number 9, I'm going to set you up that we could do the same idea. Mass of the solution is the mass of the two things combined. And then questions 5 and 6 are going to be very similar to what we did in question 4, trying to figure out how much energy comes out of the reaction.